Good afternoon, dear colleagues. Let me introduce my report called Solid Phase Formation in Ternary Systems, Metal Halides, Binary Organic Solvents. Today, the problem of the influence of chemical interactions on the shape of solubility isotherms in three-component organosalt systems, as well as on the composition and structure of compounds, crystallizing them is a poorly studied section in modern chemistry of solutions. At the same time, knowledge about solubility in multi-component systems can be used in production and in laboratory practice. For example, solvates are formed in solutions of salts of D elements, which can potentially be used as catalysts for chemical reactions, which can replace expensive and difficult to synthesize catalysts based on platinum metals. There are also known works in which properties of some crystal solvates of D elements were studied as anti-tumor drugs, as well as agents in DNA cleavage in vivo. Also, the results of such studies can be used to create an unbind model describing interactions in solution, which will make it possible to switch to directed liquid phase synthesis in inorganic compounds and materials with predicatable properties in advance, which determines the relevance of this work. This work is part of wide range of studies devoted to the study of solution-solid phase equilibrium in ternary systems containing salts of various transition metals. The aim of this work is to reveal the effects of the properties of the components on composition, structure, and conditions for the formation of crystal solvates in the system, metal halide, and binary organic solvents. The work has set the following main tasks. Firstly, determination of solubility and its change when varying the composition of mixed solvents. Secondly, determination of the composition and structure of solid phases in equilibrium with saturated solution, as well as areas of their crystallization. And thirdly, analysis of the effects of the properties of the salt component, as well as the composition of the mixed solvent in ternary system on the shape of the solution solid phase equilibrium diagrams and the structure of crystallizing compounds. In these works, chlorides and bromides of cobalt and copper were chosen as salt components, which first of all was dictated by ideology of research cycle of the last few years. These salts are readily available, stable during storage, and they are easy to obtain in anhydrous state, and solvolysis processes do not occur in their solutions. Moreover, cobalt-2 and copper-2 ions, as well as chloride and bromide ions, differ significantly in terms of softness, which makes it possible to obtain various combinations in the softness of the cation and anion. The choice of dimethyl sulfoxide and then dimethylacetamide and 1,4-dioxane as solvents is due to the following factors. They mix each other in any ratio, have different values of parameters such as dielectric constant, donor number, softness parameters, which allows focusing attention on the influence of differences in these characteristics on the balance solution-solid phase. As a tool for describing interactions in this work, we used the theory of loose acids and bases, as well as concept of hard and soft acids of bases. From the point of view of the theory of loose acids and bases, All considered cations are acids, and anions and solvents are bases. To quantify the softness or hardness of ions, Marcus proposed a method for determining this parameter. The softness parameter is positive for soft ions and negative for hard ions. The values of the softness parameters for the ions considered in this work are given in the table on the slide. For solvents in this work, such characteristics as dielectric constant, donor number, and softness according to the Marcus scale are considered as the main ones. These characteristics for solvents are shown in the tables on the slide. Let's move on to considering the main results obtained. The slide shows the isotherms of solubility as well as the structures of crystallizing compounds in the system: cobalt halide, dimethyl sulfoxide, and 1,4-dioxane. In these systems, there is a similarity in the structure of crystalline solvates in all areas of crystallization, as well as the length of these areas upon replacement of the anion in the composition of the salt compound. Thus, in these systems, 3 isostructural solvates crystallize: cobalt DMSO 6, cobalt halide 4, structure 1, cobalt DMSO 6, cobalt DMSO halide 3, 2 dioxane, structure 2. Thus, in the systems containing cobalt halides, DMSO, and dioxane, 3 isostructural solvates crystallize: cobalt DMSO 6, cobalt halide 4, structure 1, cobalt DMSO 6, cobalt DMSO halide 3, dioxane, structure 2, and cobalt halide 2, dioxane, structure 4. Solvates containing dimethyl sulfoxide as a ligand consists of an octahedral cation and tetrahedral anion, and have an insular structure. Ongoing from mixed crystal solvates to dioxanate, their structural type changes to polymeric, which is associated with the presence of 2 coordination centers in dioxane molecules. Also, in the cobalt bromide DMSO dioxane system, a solvate of the composition cobalt DMSO 6, bromine 2 DMSO of an island structure 3, is formed. If we talk about the profile of solubility isotherms, then there are significant differences. For the system containing cobalt chloride, the solubility along the entire length of the isotherm lies below the additive line. And for cobalt bromide, it's higher. In both cases, we can speak of a high contribution of cationic solvatation processes due to the high donor ability of dimethyl sulfoxide, which leads to coordination disproportionation and the formation of solvates of the island structure. When dioxane is added to DMSO, the internal structure of the latter is destroyed, which leads to the appearance in the system of free DMSO molecules with increased solvating ability. The change in solubility comparison with the additive value can be explained by different stabilization of ionic forms in solutions. In the case of cobalt chloride, acidic complexes of the type metal halide X are surrounded by harder halide anions, which leads to a decrease in their stabilization by soft DMSO molecules, which ultimately leads to ionic association and salting out. An important factor here is also the fact the dielectric constant of the mixed solvent sharply decreases even at low dioxin contents, which additionally contributes to a decrease in the solubility of a solvent. When passing to a system containing cobalt bromide, acidic complexes of the type metal halide X are formed by softer halide ions, which leads to their additional stabilization with the methyl sulfoxide molecules and further salting out. This slide shows the isotopes of solubility as well as the structures of crystallizing compounds in the system cobalt halide, dimethyl acetamide dioxide. The similarity of crystal solvates formed in ternary systems is also observed for these systems. In these systems, only individual solvates are formed containing molecules of only one solvent: islands cobalt halide 2 DMA2 and polymeric cobalt halide 2 dioxide. The cobalt halide 2 DMA2 solvate is a neutral complex, which where the cobalt ion is an tetrahedral environment. The large extent of the region of its crystallization is explained by higher donor number of dimethyl acetamide in comparison with dioxide. The solubility in these systems decreases with an increase in the molar fraction of dioxin, almost linearly, which can be explained by the fact that neutral complexes forming in the solid phase are stabilized due to van der Waals interactions with solvent molecules, and a decrease in dielectric constant does not affect solubility due to absence of ionic association process. It should also be noted that in the case of cobalt bromide DMA dioxin system, the solubility isotope in the region from 0.3 to 1 mole fraction dioxin considers with their line additive solubility. We also analyzed the change in solubility in the cobalt bromide DMSO dimer system at the same points corresponding to the values of the molar fraction amide from 0.1 to 0.2 with a step of 0.1. The solubility of the salt in this system increases with an increase of the molar fraction of DMA, reaching two local maxima points, 0.2 and 0.8, which corresponds to the point of solid phase change. The crystallization regions of different solvates were determined by X-ray phase analysis. The slide shows comparative diffraction patterns for 3 compounds crystallizing at different points of the isotherm. Let us turn to the consideration of system containing copper halides. This slide shows the isotherms of solubility and structure of solvates in the system copper halide, dimethyl sulfoxide, and 1,4-dioxane. In the system copper bromide DMSO dioxin systems, 2 individual solvates are formed: an island solvate with DMSO, copper bromide on 3 DMSO molecules, and a polymeric dioxinate, copper bromide dioxide. The solvate of copper bromide with dimethyl sulfoxide is a neutral complex in which the copper atom is in a trigonal bipyramidal environment. Bromide atoms are in equatorial positions. The similar copper chloride systems described earlier differs slightly from the copper bromide system. It also forms 2 homoligand solvates, but in the copper chloride solvate with DMSO has a polymer structure. In this case, acid complexes of the metal halide X compositions are formed by particles of different softness, which leads to decrease the strength of the complexes themselves and a decrease in their stabilization by solvent. as a result of which ionic association and salting out occurs, although it should be noted that in the case of copper bromide, this effect is pronounced less significantly due to the greater softness of the bromide anion. It is also worth noting the similarity of the profiles of solubility isotherms in the system under consideration, which can be explained by a decrease in stabilization of ionic forms in solution due to a decrease in the dielectric constant of mixed solvent. In the earlier work of our laboratory, their system containing copper chloride, DMA, and dioxin was described. The closed donor numbers of dimethyl acetamide and dimethyl sulfoxide allow one to expect similar solubility isotherms in DMSO dioxin and DMA dioxin systems. It can be expected that in both cases, a solvate containing more donor ligands will crystallize throughout the solubility isotherm, the solubility of which will gradually decrease with an increase in the 1,4-dioxin content in the system. However, the experimental results shows that in the amide system, the dependence of the solubility of copper chloride on the composition of solvent is more complex. The solubility isotherm has a local maximum, the point corresponding to the mole fraction of 1,4-dioxin 0.1. The copper chloride DMA solvate crystallizes almost throughout the solubility isotherm and only in the 0.9 to 1 region. The equilibrium solid phase is copper chloride dioxinate. The larger crystallization fields of the copper chloride DMA solvate is compared to the solvate with dioxane is associated with a higher donor number for dimethyl acetamide than for 1,4-dioxin, as in the case of systems with dimethyl sulfoxide. Consider systems containing copper halides and mixed DMSO DMA solution. The greatest variety of solvate forms is observed in the copper bromide DMSO DMA systems. In this system, 3 homoligand solvates with dimethyl sulfoxide are formed. The island composition copper bromide on 3 DMSO structure 1, the copper bromide for 4 DMSO solvates of unknown structure, and the polymer solvate with the composition copper bromide on 2 DMSO molecule structure 2. The structure of the solvate copper bromide with the dimethyl acetamide of composition copper bromide to DMA could not be determined since it was not possible to grow crystals suitable for X-ray diffraction analysis due to the high viscosity of saturated solutions. The solubility in this system changes non-monotonically. In the range of DMA content from 0 to 0.7, the solubility changes very insignificantly, after which it rises sharply, reaching local maxima corresponding to the points of solid phase change. The diagram of the solubility of copper chloride in the binary solvent DMSO DMA described earlier is shown on this slide. The isotherm consists of 2 sections of monotonic changes in solubility and has 1 local maximum in the region of mole fraction 0.7. The formation of a solvate with the composition copper chloride DMSO 2 is observed over the entire range of compositions of the mixed solvent. In the range of values of the molar fraction of amide in the systems from 0 to 0.6, the solubility decreases linearly. Comparing the profiles of the solubility isotopes and the structure of crystallizing compounds in the systems of dimethyl chloride, DMSO dioxin, one can come to the conclusion that the contribution of acid complexation processes is great in both systems because the formation constants of chlorocomplexes is in various solvents are quite large. The main processes influencing on the structural type of the solvent and determine the form of the solubility isotope are the processes of the formation of salt complexes and the stabilization of ionic forms by mixed solvents. In the case of cobalt chloride, the contribution of cationic solvatation process is also quite high, which determines the salt complexes and acidic complexes as the dominant forms in the solution. This leads to further coordination disproportionation and the formation of solvates with an island structure. With an increase in the molar fraction of dioxin, the contribution of the association process increases, the stabilization of cationic forms in solution decreases, and the type of the solid phase is replaced by a polymer one. A decrease in solubility in this case is associated with a decrease in the dielectric constant of the mixed solvents and decrease in the stabilization of ionic forms in the solution. In the case of copper chloride, the contribution of cationic solvatation by mixed solvent is much lower. Therefore, the dominant forms in solution are mixed ligand complexes, which leads to the formation of polymeric solvates and lower solubility values as compared to the system containing cobalt chloride. A decrease in solubility in this case is also determined by an increase in the contribution of the association process and a decrease in the stabilization of ionic forms in solution. In the case of the system's dimethyl bromide, DMSO dioxin, the processes occurring in the systems are similar to those considered earlier. In both systems, the contribution of acidic complexation is large due to the large values of the stability constant in bromo complexes in organic solvents compared to the chlorocomplexes. Moreover, in both systems, the contribution of cationic solvatation is large as a result of which the dominant forms in solution are soluble and acidic complexes, which contributes to the formation of solvates of the island structure and an increase in solubility in the region, relatively low contents on 1,4-dioxin, in this case of copper bromide. However, with an increase in the molar fraction of dioxin, the contribution of the association increases, the stabilization of ionic forms in the solution decreases, the dielectric constant of the mixed solvent decreases, which leads to a decrease in solubility and the formation of solvates of the polymer structure. In these systems, the solubility changes non-monotonically. There are several maxima corresponding to their retonical points. As in the previous cases, we can talk about a high contribution of acidic complexation processes and the change in the solubility and structures of crystallizing compounds will depend on the contribution of their processes of cationic solvatation and stabilization of ionic forms in solution. In the cobalt bromide DMSO DMA systems, there are two salting-in regions within which individual solvents are formed, containing molecules of only one of the two solvents and having an island structure. Within this region, predominant solvatation by one of the solvents occurs, which leads to the dominance of solvent and acidic complexation in solution, and further coordination and disproportionation. These regions are separated by section of the isotherm where salting out occurs, which can be explained by the competition of solvents for the metal center, which in general reduces the stabilization of ionic forms as a result, which salting out occurs. In the system copper bromide DMSO DMA, the contribution of cationic solvatation remains approximately the same over a range large portion of the isotherm, and copper cations are solvated predominantly by DMSO molecules due to its greater softness. This only leads to a change in number of DMSO molecules in the first solvatation shell, however, with an increase in the proportion of DMA, competition for the metal center increases and stabilization of ionic forms in solution decreases, which leads to a change in the structural type of the salt phase to a polymeric one, and then to a sharp increase in solubility and the formation an individual solvent with DMA. On this slide are presented the main conclusions. The work studied the equilibrium solution solid phase for 6 organosol systems for 25 degrees Celsius. The main results. Firstly, isotherms of solubility of cobalt and copper colloids in mixed with DMSO dioxane, DMA dioxane, and DMSO DMA were received, obtained, and characterized all equilibrium crystalline phases, and also determined the areas of their crystallization. 5 compounds were obtained in this work for the first time. 4 of them were characterized by X-ray structural analysis. The relationship of the processes occurring in the solution with the shape of the solubility isotherm, as well as their effect on the structure of crystallizing compounds in the system under consideration is shown. It is assumed that a high contribution of cationic solvatation processes leads to the formation of solvates of the island structure, while in system with the significant contribution of acidic compensation or association crystallized polymer solvents. It has been shown that the greatest total length of crystallization regions is observed for solvents containing a more donor solvent as ligand. Thank you for your attention.